Okay, so this is a big deal, metric. The idea of a metric, not just generalized but abstract idea of distance. So not only we moved from one-dimensional, two-dimensional to three-dimensional, n-dimensional space, and now we have an idea how to measure distances there. We have also we have an idea of how it might work outside of that Euclidean situation. So including graphs, as you can see here, but probably more interesting right now would be the non-Euclidean geometry. So a sphere, for example. We will, however, the kind of halfway between the two is the Taxicab metric. Okay, so I think I have it right here. Okay, so which is on one hand it is non-Euclidean. Euclidean would take it straight, and on the other hand it is kind of there is something discrete about it, such as this. You can actually do it on a graph as if it is like a grid. Okay, so in a way they are closely related. Okay, so the abstraction now, what we started doing last time was looking at the distances as functions. Okay, so the distance is a function. Okay, so to begin with, as you can see, we write dpq, which already indicates that you got to have two variables. But first, probably let's try there is only one. Okay, just to see that it is a function, and it is simple kind. Okay, so then we fix one of the two. So I replace p or q with 0. Okay, and now I'm measuring distances from 0 to any point first on the line, which gives me a function of the absolute value. So this is on x equal r. That's what the distance, Euclidean distance on a straight line, the real line, is simply the absolute value. Okay, well, once you go on to a slightly more complicated case, R2, we're still Euclidean. So, and we're talking about z equal d0, say p. Okay, p. I don't want you to think of p as of this as a function of two variables, d0, p. I want to think of p as a point on the plane. So not two variables, point on the plane, or a vector. Doesn't matter. Doesn't matter. So as we know, it will be computed by what? It will be x squared plus y squared, right? So in that sense, it is a function of two variables. It's just not. It will be confusing if you think that way until when we move on to actual metric. So you have x, y, z. Okay, and that is my function, and then as I pointed out, the graph of that function is a cone like this. A cone with 90 degrees at the base, like this. Okay, so meaning once again, you pick a point P on the plane. Okay, how? And the question, even though the question is what's the distance to the origin, origin being here, we want to force ourselves to think about this kind of thing as a function. Okay, so everything in mathematics, with all those complexities that you face, ultimately they always can be, at least to a degree, represented or interpreted as sets and functions. Okay, so I want to think of the distance as a function with a function being of what? Of a function of points. So in this particular case, there's only one point P with coordinates x, y, and then instead of trying to literally measure the distance, I have a function prepared, and I just go vertically until I hit that surface, and then I go horizontally until I find that will be z, a positive number, 0, on the z-axis. So it is a function of real value. Okay, inputs are these. and these are the outputs, the z-axis. Okay, so so if you want to visualize this in a slightly maybe more tangible way, how about level curves? Remember level curves from calculus 3? Level curves are functions of two variables. Remember what they are? Or contour curves or contour maps. Does it sound familiar to you? Maps, elevation maps. Does it sound familiar? Maps. You've seen maps with elevation, with curves indicating the same elevation. Remember that? Okay. So what is then? What are the level curves of this function? They will be circles, right? So which makes perfect sense. So these points are at the same distance from the origin, and so are these. So a concentric circle centered at the origin will give you, each of them will give you the points this many units away from the origin. Then you have as many as you like. Okay. So all right. Next dimension. I don't want to plot anything. How do we visualize this function? So once again, d0p is equal to, well, that's my function. That's my function, function of p. But this time p is in R3. So it means that it is as if it is a function. It is a function of points, but points this time they are in the three-dimensional space. How do we visualize functions? Those functions. Instead of level curves, what do we have? So, so these are 2 units from the origin. In the meantime, these are 1 unit from the origin. Okay. So that's for the plane, and then you have as many circles as you like to, on one hand, visualize this function. On the other hand, you simply visualize it makes common sense. Distance to the origin. Okay, so if it is a three-dimensional space, what do we do? All points 1 unit away from the origin. What could that be? Each of them will be, yes. Altogether, what is it? What do they form together? All points in space 1 unit away from the origin. Sphere. It's a sphere, right? So and then for each value, just like over here, you'll have this will be 1 unit away from the origin, right? And then there's a bigger one, 2 units away from the origin, like this. Okay. So it is a function. It is harder and harder as you go up the dimensions. Harder and harder to visualize. Harder and harder to. Certainly, the graphs is out of the question. Then in dimension 3 already, graph is out of the question because the graph will be 4-dimensional. And then you can still visualize it with what we call contour surfaces or level surfaces. But then you go to next dimension and then we cannot visualize it, and then we're stuck if we are not able to think abstract, and that's what mathematics is for you. So then we have to think abstract, and so we have to make sense of this thing without visualization. But this is helpful. So that's how you build intuition. You try to visualize as much as you can, for as long as you can, and in lower dimensions when still everything is tangible, and then you try to use that intuition later, or when you don't have anything tangible. So when we have an n-dimensional space, we cannot do this, but we still have a kind of a mental image that helps. Okay, so 4-dimensional space R4. Well, what's going to happen? It is hard to explain, but those won't be level surfaces for one. An n-dimensional, well, what do you say about this? It's not really not helpful. But the point was still, I was still making this simple point that distance is a function. Okay, except now it was pretty visual, but still somewhat something of a challenge when going from thinking of distances as well, we know what they are. We're measuring distance between points, and we used that in calculus, but we are moving on to this abstract point of view where the everything is a function. So we're talking about it as a function, and then turns out that this is still half of the story, because we fixed one with two values, one of the 2 points. So when we have then that 0 over there, right? I fixed it, but in general it has P and Q. Okay, so distance between two different points. So that certainly also increases the dimension of the whole thing, and so visualization is pretty much out. So that's why we have to think abstract, and that's where the where the Cartesian product comes from. So that we would not have to work too hard visualizing things that we cannot visualize. So as I said, the distance is a function, and now we define it. So what is the domain of the function? The codomain is simple. The values will be real. Okay, so that part is not going to change. So it will be always a real value, a real valued function. It is the domain that is complex. So if once again if I'm still doing a dimension 3 situation, R3, so this is still here. Okay, so I could visualize. How do I visualize functions of three variables, or value, the input of which is a point? So I could kind of label it. I could take all the points in this space and attach a number to each of them. That's what the function is. So this is 1. Why? Because the distance to the origin is 1. This is 3. This is 2. This is also 2. This may be 4, and so on. So every point in space will have a label attached to it. That label is a number, the value of the function. So if you can imagine then n-dimensional space, you can also imagine a real valued function defined in an n-dimensional space. So I mean, I don't know if this helps. 4-dimensional space, you have 4 axes. And n-dimensional space has n axes. And then once again, it's filled with points, and those points are our inputs of our function, and the attached label to each of these points will give you the value of the function. So you simply measure the distance according to our formula, and that's what you've got. Now with 2 variables, it becomes more complicated. Not 2 variables, 2 points. Distance between 2 points. It's more complicated, but it's still that's why we had all this build-up of set theory, so that we are comfortable with forming new sets as well as forming functions on sets. And so once again, so this is how it works out. So given a set, any set, okay, a metric or a distance formula, distance function, on x is a function d from x cross x to the reals to begin with. Okay, so this is the definition. So we proceed in the same manner as we did with groups. Remember, group, a set with an operation, which also was, remember, it was also a function of two variables. Yeah, right? Remember that? Where is it? Where our definition of a group. I kind of forgot that we already have faced that problem just not recently when we talked about groups. I'm just trying to find the definition of a group. Where are the groups? So this is a specific group, but I guess the groups started earlier. Here's the definition of a group. Okay, so even though we were able to skirt that problem of what is the meaning of a binary operation, this one, we just thought by analogy as an operation that is, have two elements of X taken together, and then they produce, through that binary operation, is producing another element of that set. But really it is a function. So I did mention that somewhere, but so that this function, the operation of the group, is X cross X to X, right? You see what I'm saying here? It is a function. So there's nothing mysterious about those operations. There's algebra, everything, algebra distance. We're dealing almost simultaneously with two very abstract things, but they introduce in a similar way. They're very unrelated things, as we split them up altogether from the reals. We split algebra from geometry, and but they're both of them are functions. So two elements put together give you the third. That's the algebra, or two elements put together give you a number, distance between them. So two functions. Okay, so so let's continue on with this. Just like with the group, there are axioms. There are axioms to be satisfied. So that satisfies. We already know what they are. So the first one is dxy greater than or equal to 0, called non-negativity. I think I put this together, dxy is equal to 0 if and only if x is equal to y. I'll put them together in one axiom. Number 2 is dxy is equal to dyx. So that is called the symmetry. A property that's similar, that we've seen like 3 times. In group theory, like it's similar to commutativity property, right? And they also saw it in equivalence relations as well. And finally, the triangle inequality, dxy plus dyz larger than or equal to d xz. I forgot to put the quantifiers. So, but it's for all xy here in x. This is also for all xy in x, and this is for all xyz in x. So this is it. All of these are the axioms. Okay, so the negativity is the simplest axiom to verify, that is, and that's we use the starting point is verifying that these axioms are satisfied for the particular examples that we have had, and then the second step would be to develop the theory, abstract theory, based on nothing but this definition. So we would derive conclusions, just like with algebra, from the axioms, period. Okay? So let's start with the examples, and let's demonstrate how sometimes it's easy, sometimes hard to demonstrate that the axioms are satisfied. So with R, it's certainly easy. And so is R2. So but why would be any issue involved is the triangle inequality. The first two are almost invariably have no trouble whatsoever to be demonstrated. The triangle inequality might have some challenge, and so even though the triangle inequality is known, however, if you think about it, so on the plane, take Euclidean geometry. Okay, take Euclidean geometry, the triangle inequality, which is literally what you have there, part 3. I forgot to name it. So this is a triangle inequality. Okay, so everybody knows that that is the triangle inequality, but how do you know it's true? So forget about what you have learned in this class and go back to, I don't know, middle school or something. And then you were studying Euclidean geometry, and the triangle inequality comes up. It's certainly a very simple idea, PQR, right? And then and this is so PQ. It probably roughly looked like this. Right, that's the triangle inequality and for planes. It's Euclidean geometry. It really has nothing to do with the distance formula, at least hypothetically. So we actually I did not try to do that. I did R2 instead. R2, which with our metric defined as a distance formula. So coordinates have been provided, and based on that we can prove it. But nonetheless, actually, the question still stands, even though you don't have any coordinates. You have a plane, you have 3 points, and you have your ability to measure distances. So how do we? If I don't think I want to do it, but actually anybody knows how to do it. How would you demonstrate it? That this is actually true. How did Euclid demonstrate it? I actually don't know how you demonstrate it, but just there must be a way, and so it's some geometric, and they did not heard of the Cartesian system, so no coordinates for them. The answer, I believe, is the Pythagorean theorem. At least I think so. So, I just, I'll have to. Is it going to work? So, if I cut it like this. Well, it's there is a need for a proof. So, well, let's for now call it a homework for you to do it on the plane. So Euclidean, but not Euclidean. Euclidean as in Euclid. Euclid's proof, or ancient Greek proof of the triangle inequality. Okay, so it does not necessarily fit easily into our framework, but it surely does. Instead, we're gonna pursue as planned with R2. So R2 we have then the distance formula, and then we're talking about the triangle inequality in the case of like this, 2 points, P and Q, right? This is X. I'm using the same notation, same letters, unfortunately, but I guess I'm stuck with that now. Okay, so these are the 2 points coordinates. the distance that we're trying to figure out is this. Hold on a second. We need 3 points. R. So this is x double prime. Like this and like that. Okay, so the formula is the same. Okay, the squares are the let me write the formula. It's not like we have too many choices. So PQ, I will write with squares right away. So PQ squared is equal to, okay, let me write it out. X prime minus x squared plus y minus y prime squared. Okay, now moving on. QR is squared is x double prime minus x prime squared plus y double prime minus y prime squared. Okay, and PR is squared is x double prime minus x squared plus y double prime minus y squared. Okay. Okay, so for some reason in my notes I have the Taxicab Metric proof, and I don't have the Euclidean metric proof. Okay, let's see. Yeah, it's not here. How is it? Why don't I have it here? Yeah, the triangle inequality relies now. I remember that it requires a bit more work on the Euclidean space. Actually, if I remember correctly, it involves the dot product. You actually have to have, not have to have, but probably the easiest way to have the dot product available in order to prove this. Because right now, as you can see, we're looking at the squares, not at the simply differences. Okay, so squares of the distances rather than the distances themselves. So if we try to add these together, it's not going to work out that easily. Let's see, if I just square, there will be. What happens if I square this? So it will be squares this plus square that plus twice these. Yeah, so you gotta need I'm afraid you're gonna need the dot product, and at least or the way it was done probably by Euclid, maybe law of cosines. Yeah. So well, let's talk about that next time. What I have lined up for me is the Taxicab metric. Okay, so let's assume that we know everything about Euclidean space to begin with, but the Taxicab metric isn't as easy. Not as familiar. It actually is easier in a sense. So then the plan works out just fine. So the same plan, the same picture. We just need to yeah. I just want to start with the first two axioms. Now jump to the conclusion. So dpq is equal to x prime minus x plus y prime minus y. That's all, right? Where p is equal to xy and q is equal to x prime y prime. Okay. So once again, p x, y, q, x prime, y prime. Okay, so we got to demonstrate axiom 1, which is to begin with, that part is kind of obvious, right? So part 1 of axiom 1, dpq is naturally larger than or equal to 0. So because the absolute value is always larger than or equal to 0. So that's easy. So that's non-negative property. The second property is, it does require a little bit of work, very little. bq, distance between p and q is equal to 0. That's what we're supposed to prove, if and only if p and q are the same point. Okay, so let's quickly prove that. So let's just write the formula. So x prime minus x plus y prime minus y is equal to 0. Then what? Two numbers, non-negative numbers, add up to 0, then what? First number is the absolute value, so it's non-negative. The second one is also non-negative. So, but they add up to 0. What does it tell you? They reach 0. Yeah. So then x prime minus x is equal to 0. Y prime minus y is equal to 0 because both are non-negative. Okay, and then it turns out that we are using what we're about to use is the same property for dimension 1. For dimension 1, so if the absolute value of any number is equal to 0, that number is 0. Okay, then x prime minus x is equal to 0, y prime minus y is equal to 0, minus prime is equal to 0, or x prime is equal to x, y prime is equal to y, or p is equal to q. End of proof. Okay? So, like I said, in the middle we break it coordinate-wise, between x and y's, but then we start talking about the two x's separately, but each of the x's is on the Euclidean space of its own, and it has the same property. We are indirectly using the axiom 1 for R. Okay, so where is it? This one. Using just a comment using axiom 1 for R twice. Right? So well, here, more like over here. So when the distance between x and x prime is equal to 0, it means that it's the same number, same point. Okay. So okay, now axiom 2. That's easy. So dpq is equal to x prime minus x. I mean, it's very easy once you do it once, okay? But you still have to do it once. Plus y prime minus y. Okay, it is the same as x minus x prime plus y minus y prime, right? Which is dqp. That's the symmetry, right? And furthermore, just like in the last one, over here we implicitly using axiom 2 for R. So once again, it's just not part of the proof, but it is a comment worth making. So, but by design, what is happening is that the distance formula for R is used to build distance formula for R2 and for R3 and so on. Okay, and then the properties of the metric property of this distance formula is used then to prove what we need to prove about the high-dimensional Euclidean spaces. Okay, so let's do the let's do axiom 3. Axiom 3. So once again we're back to this problem of having several points of 3 points. So that certainly expands the how much we have to deal with this. Okay, so say I have like that once again. I will writing out again P, Q, and R. Once again, this is x, y, x prime, y prime, x double prime, y double prime. Okay, so and then once again I need to prove the triangle inequality. Okay, so let me try to maybe visualize it first. So that's the problem. So I don't want to diminish this. So I'll put it here in the box of what we're supposed to prove. Well, let me write what we're supposed to prove. So d p cube, once again d qr larger than or equal to d pr. Okay, so that's the triangle inequality. Triangle inequality to be proven here. So what I'm gonna try to do now, I'll try to illustrate this idea. Yeah. Okay. So let's add the axes. Okay, so I'm adding axes like this. Oops. X and Y. Okay, so as I have done before, so x prime, y x double prime, and here I have y prime, y double prime. Okay, so we can actually plot the 3 terms. Okay, so each of them is let's write it out over here. So this will be x prime minus x plus y prime minus y. Okay, let's find them on my graph. So x prime minus x prime minus x is this. Okay, and y prime minus y is that. Okay, these are the 2 distances in the first term. Now I'm going with the second term. So it will be x double prime minus x prime plus y double prime minus y prime. Okay, let's find these. So the orange terms are here. I plotted them. The blue, let's make these blue. So x double prime, this one. And where's the other one? Well, the prime, so this one. Okay, and the third, this is the one. It is what it is, x double prime minus x plus y double prime minus y. Okay, where are those? Make them green. X double prime minus x, so this is the one. And y's is this. So what is the, how do we combine these? So the left-hand side, so the blue and orange are combined together. I'm not sure if it is, so blue and orange are combined together and to be compared with green. Okay, any observations that you want to make? So once again, there's a big plus over here. Two orange terms and two blue terms compared to the two green terms. Let's do one axis at a time. Let's just look first at nothing but the x-axis. Okay, what can you say? So in other words, I'm looking at this one, this orange, and this one, and that one. Any thoughts? Orange plus green versus orange plus blue versus green. What do you see?
Orange plus blue equals green?
They seem to be the same. Yes. So so once again, x prime minus x plus x double prime minus x prime seem to be the same as well. They are not only seem to be the same, they are the same as far as picture is concerned. Why it is not the end of the story, we'll just see in a moment, and that is as soon as we look at the y-axis, we realize that this is not the end of the story. What is happening with the same question, but now for the y-axis. So orange plus blue is compared to green.
Orange minus blue would give you green?
No, or look at the picture of the formula at the top. Orange plus blue, supposed to be, is it larger than or equal to the green term? So those intervals that I painted are the ones to be compared. So orange, blue, plus compared to green. What can you say about that? Seems to be bigger, strictly bigger. So that's what we are seeing here. So so we're talking about then y prime minus y plus y double prime minus y prime seems larger than y double prime minus y. So it doesn't have to be either equal to the same, or it doesn't have to be the same, but it should be probably larger. So on what grounds we would say we would like this would be good enough for us. We don't really need the same. If it is larger, we are fine with it. So so the picture does provide evidence or in support of our conclusion. So it is either the same or larger, those two expressions. So if we take x and y axis separately, we did, and then we make the conclusion that we want, we put them together, the inequality will be provided, right? So it's still orange plus blue twice, and then larger than or equal to green appearing twice. Okay, so we cannot say that they are equal to, but we might be able to conclude that they will be larger than. So on what grounds? Because this is a particular example, P and Q and R are arranged in a particular way relative to each other, and so that's, for example, P, the first one, is below everybody as well as to the left of everybody. If you flip them, the conclusions that we draw over there would be different. So the idea, what's the idea then? Look at the idea over here. We proved the two axioms, and we will prove them straightforwardly. But the comment actually becomes important. These two comments become important. That we actually used axioms to prove axiom 1. We used axiom 1 for R. To prove axiom 2 for R2, we used axiom 2 for R. So that is the idea once again. The idea is use axiom 2, 3 for R twice. So it's all about using it twice, or as many as, so twice. These two were used also twice each. Okay, so that is the idea for x. So we apply axiom 3 for the x-axis, and we apply axiom 3 for the y-axis. And then we add them together. Okay, so that's the plan. So once again, the picture is convincing if you are really willing to accept it, and it is tempting to just accept it because it's so visual, but that does not constitute a proof, because the picture that is always not, you can always rearrange things, and the formulas that, the conclusions that you try to draw based on the pictures might be not exactly the same. So you don't really know. You could try to consider all possible cases and then that make that conclusion, but I think it is more profound idea is to actually recognize that we're talking about simply the axiom 3, the triangle inequality for the axes. Okay, so let's forget the picture, and let's just say this: x prime, x double prime in some order. So on the x-axis. Okay, that's all. We don't know what that order is, but no matter what that order is, what do we know? No matter. So we use the triangle inequality for R. So triangle inequality, the only matters is that we progress from x to x prime, from x prime to x double prime. So what is it? It is x prime minus x plus x double prime minus x prime is larger than or equal to x double prime minus x. That is the triangle inequality for R. Okay, and then same for, so that's for the x-axis. And then secondly, we do the same for the y-axis. So we'll just do it next time, but pretty much it will fall into our lap.